Our universe is vast, an endless ocean of stars and mysteries. From our small planet, we've long gazed outward, seeking to understand our place in the cosmos. Sometimes the universe sends us a message, a cosmic bottle washed ashore. Interstellar objects, visitors from other stars, offer us rare glimpses into distant worlds. Each is a precious sample, a time capsule from another solar system. These cosmic messengers connect us to the greater galactic story. For centuries, we believed everything in our skies belonged to our sun. Then, in 2017, everything changed. Astronomers spotted an object moving in a way they had never seen before. This was our first confirmed interstellar guest, Oumuamua. It was a puzzle from the very beginning. Just 2 years later, in 2019, a second interstellar visitor was found. This one was named 2I Borisov. Unlike Oumuamua, Borisov looked and acted much more like a traditional comet. The space between stars is not empty. It's filled with wandering objects, the nomads of the galaxy. The cosmos had another delivery for us. On July 1st, 2025, the Atlas telescope in Chile discovered a faint, unknown object. Its path a wide-open hyperbola, the unmistakable signature of an interstellar traveler. Officially named 3I Atlas, this visitor gives us time, months, maybe years, to study a messenger from the stars. Its arrival marks the start of a new quest to unveil the secrets of our cosmic neighborhood. For most of history, we thought our solar system was all there was. That changed in October 2017, when a telescope in Hawaii spotted Oumuamua, a mysterious object from another star. Its hyperbolic path showed it was just passing through, not bound to our sun. Oumuamua's odd shape and unexplained acceleration baffled scientists. Like a message in a bottle, it left us with more questions than answers, and a new search for interstellar visitors. Just 2 years after the fleeting passage of Oumuamua, the cosmos sent another traveler our way. In August 2019, an amateur astronomer in Crimea named Gennady Borisov spotted a new comet. As professionals around the world turned their telescopes to track its path, they confirmed the incredible. Its orbit was strongly hyperbolic. This was it, our second confirmed interstellar visitor. Named 2I Borisov in honor of its discoverer, this object presented a stark contrast to its predecessor. Where Oumuamua was a strange, rocky enigma, Borisov looked and behaved in a much more recognizable way. It was, quite clearly, a comet, complete with a fuzzy halo of gas and a long, streaming tail. The discovery of 2I Borisov was a monumental moment for planetary science. Unlike the brief glimpse we got of Oumuamua, Borisov was detected on its way into the solar system, months before its closest approach to the sun. This gave astronomers a precious, extended window of time to study it in detail. Major observatories, including the Hubble Space Telescope, were mobilized to analyze the light coming from its coma. For the first time, we could perform a detailed chemical analysis of the material vaporizing from an object that formed around another star. It was like getting a direct sample of the building blocks of another planetary system. The results of these observations were fascinating. Spectroscopic analysis revealed that 2I Borisov's coma contained familiar substances like water and dust. However, it also showed some intriguing chemical quirks. Most notably, it had an unusually high concentration of carbon monoxide gas compared to the comets from our own solar system. This suggested that Borisov likely formed in a very different environment than our own comets, perhaps in a much colder region around its parent star, or around a different type of star altogether, like a cool red dwarf. It was a familiar stranger, recognizable as a comet, yet carrying a distinct chemical fingerprint of its alien origin. 2I Borisov provided a crucial piece of the puzzle. It demonstrated that comet-like bodies, similar to those that may have delivered water and organic molecules to the early Earth, also exist in other star systems. It confirmed that the fundamental ingredients for planets, and perhaps for life, are not unique to our little corner of the galaxy. While Oumuamua showed us how strange and diverse interstellar objects could be, Borisov showed us how similar they could be as well. Together, these first two visitors set the stage, preparing us for the next arrival and the deeper questions it would allow us to ask. The back-to-back discoveries of Oumuamua and Borisov opened a new window onto the galaxy. They transformed the study of interstellar objects from a theoretical exercise into a vibrant, observational field of astronomy. The first and most profound lesson was simply that these visitors are a regular feature of our cosmic neighborhood. Based on the detection rate of these first two, astronomers now estimate that at any given time, several interstellar objects are likely passing through our solar system, most too small and faint for us to see with current technology. The space between stars is not an empty desert. It's a dynamic highway of wandering worlds. These two messengers also taught us about the sheer diversity of objects forged in other stellar nurseries. Oumuamua was a rocky, dry, and strangely shaped enigma. Borisov was a more conventional, icy comet, yet with its own peculiar chemistry. This contrast implies that the planet-forming disks around other stars can produce a wide variety of small bodies. Some systems may be more efficient at ejecting rocky fragments, while others may cast out icy comets. Each new visitor adds another data point, helping us build a more complete picture of the demographics of worlds across the Milky Way galaxy. Furthermore, the study of these objects provided a powerful, if challenging, new tool for galactic archaeology. Comets and asteroids are pristine relics from the time of planet formation. By studying the composition of an interstellar object, we can learn about the chemical environment of its home star system without ever having to travel there. For example, the high carbon monoxide content in Borisov hints at the conditions in its birthplace. With enough visitors, we could begin to map the chemical diversity of different regions of our galaxy, understanding how the raw materials for planets vary from one stellar population to another. Finally, the experience with our first two interstellar guests was a crucial dress rehearsal for the future. The frantic, short-lived campaign to observe Oumuamua highlighted the need for rapid response observing strategies. The more successful, longer-term study of Borisov demonstrated the immense value of early detection. These lessons drove improvements in our sky survey capabilities and fostered a global network of astronomers ready to spring into action. The astronomical community was now primed and waiting, armed with better tools and refined questions, ready for the next message to wash up on our cosmic shore. On the peaks of the Chilean Andes, robotic telescopes like Atlas stand guard under the clearest skies on Earth. Their mission: to scan the heavens for asteroids or comets that could threaten our planet. Atlas's automated cameras sweep the sky, searching for anything that moves or changes. Software compares images, flagging moving objects, asteroids, comets, or something entirely new. It's a cosmic dragnet, always watching, ready to catch the extraordinary. The 1st of July, 2025, began like any other day for the global network of astronomers. Data from the night's observations flowed from telescopes in places like Chile and Hawaii to data centers around the world. Buried within this torrent of information from the Atlas telescope at Rio Hurtado, Chile, was a sequence of images containing a single, faint point of light that hadn't been there before. The automated software did its job flawlessly. It detected the new object, noted its movement against the background stars over several observations, and assigned it a temporary designation. At this initial stage, it was just another anonymous blip, one of many potential new discoveries made that night. As the initial data points were collected, the first tentative orbit was calculated. This is a routine process, a simple mathematical exercise to connect the dots and get a rough idea of the object's path through space. The first result was likely intriguing but not yet definitive. The orbit appeared unusual, highly elongated. This could mean many things. It might be a long-period comet from the farthest reaches of our own Oort cloud, on a journey taking millions of years to complete. Such comets have orbits that are almost, but not quite, unbound from the Sun. More data was needed to be certain. The crucial work began as astronomers looked back through archival data. This process, known as a pre-discovery search, involves scouring images taken in the preceding days and weeks to see if the object had been accidentally captured before its official discovery. They found it. Faint traces of the object were present in images stretching back to at least the 14th of June. Each of these older data points was a priceless new piece of the puzzle. With a longer arc of observation, the orbit could be calculated with much greater precision. The more dots you have, the more clearly you can draw the line that connects them. With this new, more extensive set of observations, the true nature of the object snapped into sharp focus. The uncertainty shrank, and the conclusion became inescapable. The object's path was not a very stretched ellipse. It was a clear and unambiguous hyperbole. Its eccentricity, a measure of how much an orbit deviates from a perfect circle, is significantly greater than 1. This was the smoking gun. This object was moving too fast to be captured by the sun's gravity. It was not from our solar system. It was a visitor, a traveler from the interstellar void. The third messenger had arrived. The confirmation of a hyperbolic orbit electrified the astronomical community. The Minor Planet Center announced the discovery, and alerts went out worldwide. A new interstellar object had arrived. Designated 3I Atlas, it was soon confirmed as a comet, sparking a global campaign to observe this rare visitor. News spread fast, igniting excitement among scientists and the public alike. This was not a warning of danger, but a call to discovery. The investigation had begun. The discovery of 3I Atlas was special, not just for what it was, but when it was found. Unlike Oumuamua, it was spotted early, giving astronomers the priceless gift of time. With months to prepare, scientists could plan detailed observations, track its journey, and unlock secrets about its origins. Early detection turned a fleeting glimpse into a scientific treasure. Every object in our solar system, from Jupiter to the tiniest dust, follows a path shaped by the sun's gravity. Most orbits are closed loops, circles or ellipses, binding planets and comets to our star. But 3I Atlas follows a hyperbolic path, a one-way journey from interstellar space. It swings past the sun, never to return, proof it's not from our solar family. Its fleeting visit links us to the vast galaxy beyond. Three I Atlas races through space at over 220,000 kilometers per hour, far faster than anything in our solar system. Launched by a distant event, it now plunges toward the sun, gaining speed as gravity slingshots it around our star. After its closest approach, it will slow and fade, returning to interstellar space, its journey through the Milky Way continuing as before. When a new comet or asteroid is discovered, the first question is always, is it coming near us? For 3I Atlas, the answer is a reassuring no. Its path keeps it millions of kilometers from Earth. Its orbit is tilted, passing through our solar system at an angle, far from our planet's path. There's absolutely no risk of impact. We can observe it with pure curiosity. This safe distance is a lucky result of orbital mechanics. Direct hits are incredibly rare. Instead of panic, astronomers can focus on unraveling its mysteries. 3I Atlas's safe passage turns a potential threat into a unique scientific gift. Three I Atlas's visit is brief for the cosmos, but a drawn-out event for us. After its closest approach to the sun, it will slowly fade as it journeys back into deep space. Astronomers will track its fading light for months, maybe years, squeezing out every last bit of data. As it crosses the orbits of distant planets, its coma will dissipate, revealing more of its core. Eventually, it will slip beyond Neptune, becoming a faint ghost detectable only by our most powerful telescopes. The data gathered will fuel research for decades, deepening our understanding of the galaxy. Its fleeting passage connects us to the vast cosmic ocean. How big is 3I Atlas? That's a tough question. Its nucleus is hidden inside a glowing coma of gas and dust. Measuring its true size is like spotting a firefly in a chandelier. Astronomers rely on clever indirect methods. Estimates range from a few hundred meters to several kilometers across. Its size hints at its origin, either a massive ejection or a fragment of a larger body. Its speed is staggering, over 61 kilometers per second, far faster than any human-made probe. This velocity confirms its interstellar origin and hints at a violent past. Every observation helps refine our understanding of this mysterious traveler. 3I Atlas is a true ghost in the darkness, defined by speed, shrouded in mystery. The most striking feature of 3I Atlas is its spectacular display as it nears the sun. Dormant for eons, it awakens as sunlight triggers its ices to sublimate, forming a glowing coma and dramatic tails. These tails, one of gas, one of dust, stretch for millions of kilometers, revealing its composition. The activity confirms it's rich in volatile ices, similar to comets from our own solar system. By tracking how its outgassing changes, astronomers decode the types of ices and their origins. Each flare and flicker is a chemical signal from another star system. With modern telescopes, we can watch this process in unprecedented detail. 3I Atlas's fiery breath is a rare, real-time glimpse into the chemistry of another world. The light from 3I Atlas is a coded message, decoded by spectroscopy. By splitting its light, astronomers identify the unique chemical fingerprints of its gases and dust. Water, carbon monoxide, and carbonyl sulfide are among the familiar ingredients, echoes of our own comets. But subtle differences in the mix reveal its alien origin. Each new detection adds to the recipe for building planets around another star. These chemical clues help us compare our solar system to others. For the first time, we're getting a detailed ingredient list from a distant world. Among 3I Atlas's ingredients, one stands out: an unusually high abundance of carbon dioxide. Its CO2 to water ratio is far higher than in typical solar system comets, a fundamental difference. This suggests it formed in a much colder region, or around a cooler star. The chemistry acts as a thermometer, revealing the climate of its home system. This discovery challenges our models of planet and comet formation. 3I Atlas shows that cosmic recipes vary widely, hinting at new possibilities for planet formation and life. One chemical anomaly opens a whole new line of inquiry into the diversity of worlds beyond our own. Beyond its immediate composition, the journey of 3I Atlas holds clues to its age and its deep past. By tracing its trajectory backward out of the solar system, astronomers can determine the direction in the sky from which it came. This points to its origin within the Milky Way galaxy. The initial calculations suggest that 3I Atlas came from the direction of what is known as the galactic thick disk. Our galaxy has different components: a thin disk where young stars like our Sun are actively forming, and a surrounding, older, and more spread-out thick disk. This is a profound clue. If 3I Atlas truly originates from the thick disk, it means it was likely born around a much older star than our Sun. The stars in the thick disk are ancient, some of them billions of years older than our 4.6 billion-year-old solar system. This implies that 3I Atlas could be an incredibly old object, a pristine relic from a much earlier epoch of the galaxy's history. It might have been wandering through interstellar space for billions of years before its chance encounter with our Sun. It is not just a visitor from another place, but potentially a visitor from another time. This potential antiquity makes the comet even more precious. It would be a sample of the raw materials that were available for planet formation in the galaxy billions of years ago. The chemical composition of the galaxy evolves over time, as generations of stars live and die, creating heavier elements and seeding them back into space. By studying the elemental and isotopic ratios in 3I Atlas, we could get a direct glimpse into the chemical environment of the Milky Way as it was in the distant past. It would be a form of galactic archaeology, using a physical artifact to study a bygone era. Imagine holding a rock that is twice as old as the Earth itself. That is the potential significance of 3I Atlas. It is a time capsule, carrying information not just about its parent star, but about the state of the galaxy when that star was young. Its long, lonely journey through the void has preserved it, with cosmic rays slowly baking its surface, but leaving its deep interior frozen and unchanged. As we unveil its secrets, we are not just looking at a piece of another solar system. We are looking back in time, reading a message from the deep past of our own Milky Way galaxy, delivered to us by an ancient silent wanderer. The discovery of 3I Atlas sparked a global scientific campaign, a coordinated effort spanning continents and observatories. Astronomers worldwide worked together, sharing data in real time, passing the baton of observation as Earth turned. This rapid collaboration ensured no event was missed, uniting specialists from every field. The quest to understand 3I Atlas became a shared human endeavor, transcending borders and uniting us beneath the stars. To study distant objects like 3I Atlas, astronomers use a powerful array of telescopes and instruments. Wide-field surveys find targets, while giant ground-based and space telescopes reveal their secrets. Instruments like spectrographs and polarimeters decode the light, uncovering the comet's composition and structure. Together, this technological symphony lets us unveil the mysteries of the cosmos. All the data gathered by this global network of telescopes is just the beginning of the journey. The streams of ones and zeros, the images and spectra, are raw information. The real work of science is to turn that information into knowledge. This means connecting the dots. It involves meticulous analysis, careful comparison, and the building of new theories to explain what is being observed. For 3I Atlas, this process happens in several stages, each one building on the last. The first step is to precisely map its journey, refining its orbit with every new observation to predict its future path and trace its past. Next, scientists focus on the physical properties. By combining the measurements of brightness, the rate of gas production, and the amount of dust, they can create computer models that simulate the comet's behavior. They might ask, if a nucleus of a certain size and composition were heated by the sun, would it produce the coma we see? By tweaking the parameters of the model, size, reflectivity, ratio of ice to rock, and comparing the simulation to the real observations, they can slowly zero in on the most likely characteristics of the hidden nucleus. It's a process of elimination, a way of solving a puzzle by testing every possible solution against the evidence. The most profound connections are made when the composition of 3I Atlas is compared to other objects. How does its CO2 to water ratio stack up against the dozens of solar system comets we have studied? How does it compare to the carbon monoxide-rich composition of 2I Borisov? By placing 3I Atlas into this broader family context, we can start to see patterns. We can begin to classify interstellar objects, perhaps finding that there are Borisov-type visitors and Atlas-type visitors. This comparative analysis is what turns a single, fascinating discovery into a new field of science, allowing us to understand the range of possibilities for planetary building blocks across the galaxy. Ultimately, connecting the dots means weaving all of this information into a single, coherent story. It's a story that starts with the formation of the object around a distant, ancient star in the Milky Way's thick disk. It continues with its violent ejection into interstellar space and its long, dark journey through the void. And it culminates in its brief, spectacular passage through our solar system, where its secrets are finally revealed by our watchful eyes and powerful tools. Every observation, every analysis, every theory is a word in that story, a story that 3I Atlas has carried across space and time to deliver to us. The passage of 3I Atlas through our solar system is a profound reminder of our connection to the wider universe. These interstellar visitors are messengers, carrying clues from distant worlds. Their journeys challenge our assumptions, inspire global collaboration, and drive us to innovate. As we bid farewell to 3I Atlas, we are reminded the universe is vast, and there is always more to discover.